Hey everyone, and welcome. Today we're going to do a deep dive on shape memory materials.
Ooh.
These are fascinating materials that can actually, get this, remember their original shape.
Yeah, and we'll be taking a look at both shape memory alloys,
And
shape memory polymers.
we've got a ton of cool research to dig into today.
Definitely so many incredible ways these materials are being used.
I know. But first, can we just start with the basics? Like, what exactly are these shape-shifting metals? I'm picturing some super high-tech,
Yeah.
sci-fi stuff.
Right, well, they're called shape memory alloys, or SMAs, and the key is it's their ability to go back to their original shape, even after they've been deformed, twisted, bent.
Wow.
Yeah, it all boils down to this cool interplay between two phases in their structure,
Okay.
austenite and martensite.
Those names sound kind of intimidating.
I know, but think of austenite like the metal's stable state at higher temperatures.
Okay.
It's like a really neat and ordered structure.
Gotcha.
But when you cool it down,
It transforms into martensite. This is the low temperature phase, and it's way more flexible. It's like those neat, orderly atoms become all jumbled up.
So it's like if I bend a paper clip,
Yes.
I'm changing the shape,
Exactly.
but it wants to spring back, right?
Yeah, like that's a perfect analogy.
So is that kind of like what's happening
so
with the martensite?
When you deform martensite,
Yeah.
you're shifting those atoms around, but they're not permanently messed up.
Okay.
It's like
So
temporary.
they're just waiting to go back to that.
Right.
Yeah.
And when you heat the SMA back up, it's like giving it a burst of energy to go back to that austenite structure.
Like a reset button?
Yeah, exactly.
Wow, that's incredible.
Yeah, the material just like remembers its original shape.
That is so cool.
And there are different types of metals that do this, like nickel titanium.
Ooh, nickel titanium. Now that sounds like it's from the future.
It is pretty amazing.
Yeah.
It's also called nitinol. Okay.
And it can handle a lot of deformation before bouncing back.
Hmm.
Plus, it's strong, it resists corrosion, and it's even biocompatible.
Wow.
Which is why it's often used for, medical implants and things.
Oh, okay, so that makes sense.
Yeah.
And what about, you mentioned there were other metals.
Yeah, copper, zinc, aluminum is another common one.
Hmm.
This one's great because it's a bit more budget friendly.
Gotcha.
And it's really good at absorbing shocks and vibrations.
So like a shock absorber.
Yeah, exactly. So it's really useful for things like machinery or tools where you want to reduce those unwanted movements.
Okay, so we're already seeing like a lot of variety here.
Yeah, definitely.
And how these metals can be used.
Absolutely.
But hold on, I've also heard about shape memory polymers, or SMPs.
Oh yeah, SMPs.
Are those kind of similar, or is that something totally different?
They are similar in the sense that they can also remember their shape.
Okay.
But instead of relying on those crystal structures in metals,
Right.
they use the arrangement of these long chains of molecules called polymers.
Polymers.
Yeah.
Okay, so it's the same basic idea,
Mm-hmm.
but it's happening on like a much smaller scale.
Exactly.
Interesting.
And that leads to some interesting differences. Well, for one, SMPs are way cheaper to produce.
Excellent.
And they're super lightweight. Plus, they can handle even larger deformations before going back to their original shape.
Wow. Okay, now that is impressive.
Right.
So what triggers that change? Is it still heat, like with the SMAs?
Well,
or is it something different?
this is where things get really interesting with SMPs because they can be triggered by a whole bunch of things.
Like what?
Heat? Yeah, but also light.
Oh, wow.
Even changes in pH.
What? Really?
Yeah, so they can be designed to respond to really specific conditions.
Like they're super sensitive
yeah,
to their environment.
to their surroundings.
That's amazing.
Yeah.
But let's talk about how all of this is being used in the real world.
Okay, yeah.
I'm especially curious about the medical applications.
Yeah.
Like imagine tiny implants that can change shape inside the body.
Yeah, that's actually happening right now with things like self-expanding stents.
Oh, yeah, I've heard about those.
Yeah, they're inserted into blocked blood vessels in a compressed form.
Right.
And then when they're exposed to body temperature, they expand to open up the blood vessel.
So it's a much less invasive way to treat blockages.
Yeah, much less invasive than traditional surgery.
Wow. Okay. And what else?
And that's just the start. There are orthodontic wires for braces that use SMAs.
Okay.
They apply gentle, constant pressure to the teeth.
So they're more effective.
Yeah, and more comfortable.
Makes sense.
And SMPs are being explored for biodegradable implants.
Oh, wow. So they would just dissolve
Yeah.
after they've done their job.
Exactly.
That's amazing. You wouldn't need another surgery.
Exactly. No more surgery to remove them.
Wow. That's incredible. Are there any other cool medical applications?
There are so many. One really exciting one is a new type of bone screw.
A bone screw?
Yeah, it's made from a shape memory composite, and it's inserted in a compact form.
Okay.
And then it self-expands to fix the bone.
Oh, wow.
But that's not all.
What else?
It also promotes bone growth, and it's flexible enough to allow natural bone movement while still providing support.
Wow, so it's like a super bone screw.
It really is.
That's amazing. Seems like shape memory materials are really changing the game in medicine.
Yeah, they definitely are.
But what about other fields? I mean...
Oh, yeah, we're just getting started.
There's got to be more.
So many more applications, like aerospace, robotics, even making our cars smarter.
Ooh. Okay, well, let's dive into all of that.
Let's do it.
After the break.
Sounds good. Welcome back. I'm ready for more shape-shifting adventures.
Me too. I'm still blown away by all those medical applications we talked about.
Yeah, it's incredible how SMAs and SMPs are already making a difference in people's lives.
Definitely. But before we jump into more applications, I kind of want to go back to the basics for a minute.
Sure.
We talked about how heat triggers those SMAs to go back to their original shape.
Right.
But what's actually happening at the, atomic level?
Oh, that's a great question. It all boils down to those crystal structures we talked about.
Okay, so like those perfectly stacked blocks of austenite.
Exactly. Now, when the SMA cools down and becomes martensite, the atoms shift a little bit, and they create these things called twins.
Twins? Like identical atoms, but in different spots?
Yeah, you got it. It's like looking in a mirror.
Okay.
These twins are regions where the atoms are arranged in mirror images of each other.
Interesting. So when you bend or deform an SMA...
Yeah.
Are you, moving those twin boundaries around?
Exactly. That's what causes the material to change shape.
Okay.
But the cool thing is that atoms themselves aren't permanently messed up.
It's temporary.
Yeah, just a temporary shift.
So they're just kind of hanging out, waiting to go back.
Exactly. And when you heat it back up, that heat gives those atoms the energy to snap back to their original positions.
Like those neat little blocks again.
Exactly. And as those twin boundaries disappear...
Yeah.
The material goes back to its original shape.
Wow, that's amazing. So how much can you actually deform an SMA before it, forgets its shape?
Well, most SMAs can recover from strains of up to 8%.
8%? That seems like a lot.
It is. Imagine bending a metal rod into a U shape. That's about 8%.
Oh, wow. Okay. But does that shape memory ever wear out?
Well, nothing lasts forever.
Right.
But SMAs are pretty durable. They can go through thousands, even millions of cycles. But of course, extreme temperatures or constant stress can affect them over time.
That makes sense. So it's not like a magic material.
Yeah.
Okay, so we've talked a lot about SMAs, but what about SMPs? How does their shape memory work?
That's a great question. And it is different from metals.
Okay.
Remember those long polymer chains we talked about?
Yeah, like a tangled mess of strings.
Exactly. Well, in SMPs, those chains are actually connected to each other at certain points.
So like knots in the strings.
Exactly. And these connections are key to the shape memory effect.
Okay, so how does that work?
So SMPs have this thing called a glass transition temperature.
Okay.
Below that temperature, the polymer is rigid, like hard plastic.
Gotcha.
But when you heat it up above that temperature,
yeah,
the chains loosen up and become much more flexible.
So it's like the heat is untying those knots.
Yeah. And if you deform the SMP while it's flexible and then cool it down, it'll stay in that new shape.
Oh, so it's like molding clay.
Exactly. And those connections we talked about act like anchors.
They hold the chains in their new positions.
Exactly. And then when you heat it back up again,
yeah,
those chains can move again.
Okay.
And they're pulled back to their original positions by those anchor points.
So the SMP goes back to its original shape.
Precisely.
Wow. So the memory is stored in those connections.
Yeah, you could say that.
That's really cool. So what are the advantages of using SMPs over SMAs?
Well, first of all, SMPs are much cheaper to produce.
That makes sense, especially for making a lot of something.
Right. Plus, they're incredibly lightweight, and they can recover from way larger deformations than SMAs.
Like how much larger?
We're talking up to 800% or even more.
800%? That's insane.
Yeah, it's pretty incredible.
Are there any downsides to using SMPs?
Well, they're not as strong as SMAs.
Okay.
So they might not be the best choice for heavy loads or repeated stress.
Makes sense. You got to pick the right material for the job.
Exactly.
Yeah.
And sometimes the recovery time for SMPs can be a bit slower.
So it's not always instant.
Right. It takes time for those chains to rearrange themselves.
Okay. So what about those other triggers for shape memory in SMPs?
Oh, yeah. There are some really cool ones.
Like what?
Well, there are light-responsive SMPs.
So you can shine a light on it.
Yeah.
And it changes shape?
Exactly.
That sounds like sci-fi.
I know, right? But
Yeah.
it's becoming a reality. Wow. Imagine medical implants that can be activated by light.
That would be amazing.
Yeah, no more invasive procedures.
What other triggers are there?
There are also electroactive SMPs.
Right.
They respond to electric fields. So they're great for things like artificial muscles.
Like a robotic arm that moves like a human arm.
Exactly. And then there are magnetoactive SMPs.
Magnetoactive?
Yeah, they have tiny magnetic particles in them.
Oh, wow.
So you can control them with magnets.
That's so cool.
It opens up so many possibilities, especially for robotics.
It's like we're living in the future.
I know, right? And we're just scratching the surface.
I can't wait to see what they come up with next.
Me too. In the next part, we'll delve into even more futuristic applications like self-healing structures and energy harvesting devices.
Ooh, that sounds amazing.
Yeah.
Let's take a break and then dive into that. Welcome back. So much cool stuff about shape memory materials.
I know, right? It's mind-blowing.
Yeah, from those tiny little stents to robots that can be controlled with magnets. It's incredible.
And we're not done yet. Remember those futuristic applications I mentioned?
Oh, yeah. Self-healing structures.
Yeah.
And energy harvesting.
Exactly. Let's start with self-healing.
Okay.
Imagine a bridge that can repair cracks on its own.
That would be amazing. How does that even work?
It's all about embedding tiny capsules filled with a healing agent.
Into the material?
Yeah, like into a polymer or even concrete.
If the material gets damaged,
those capsules break open, release the healing agent.
So it's like a built-in first aid kit.
Yeah, exactly. And here's the cool part.
What?
That healing agent is often a shape memory polymer.
Oh, wow.
So when it comes in contact with the damage, it's triggered by heat or light to flow into the cracks and then harden.
So it basically stitches itself back together.
Exactly.
That's insane. Where could we use something like that?
Oh, so many places. Self-healing bridges, buildings that can repair earthquake damage, airplane wings that can fix themselves during flight.
It would make everything so much safer.
Yeah.
And more resilient and reduce maintenance costs.
Wow. What about energy harvesting? How do shape memory materials play a role there?
So SMAs can actually convert heat energy into mechanical energy.
Wait, really? How?
Remember how heating an SMA makes it contract?
Yeah.
Well, we can use that contraction to do work, like turning a generator.
So the shape change creates electricity.
Yeah.
That's incredible. And where does the heat come from?
All sorts of places. Waste heat from factories, solar energy, even body heat.
Wait, you mean we could power devices using our own body heat?
Exactly.
Yeah.
Imagine a smartwatch that never needs charging.
That would be a game changer. It seems like shape memory materials are not just cool, but also super important for the future.
Yeah, they have the potential to solve some big problems.
Like finding new sources of energy.
Absolutely.
So what else is on the horizon for these amazing materials?
Oh, so much. Targeted drug delivery systems, tiny robots for surgery, even clothes that can adapt to temperature changes.
Wow. But I imagine there's still some challenges, right?
Yeah, definitely. Like what?
Well, some of these materials are still pretty expensive to make.
Makes sense. New technology is always expensive at first.
Right. And durability can be an issue. They don't last forever.
Yeah, I guess nothing does.
And controlling those shape changes precisely can be tricky.
So there's still a lot of work to be done.
Yeah, but there are tons of researchers working on these challenges.
It's exciting to think about all the possibilities.
Absolutely. I can't wait to see what the future holds for these materials.
Me too. This has been an amazing deep dive into the world of shape memory materials.
Thanks for joining me.
And to our listeners, thank you for tuning in. We hope you enjoyed learning about these incredible materials. If you want to explore more, be sure to check out the show notes for links to some of the research we discussed. Until next time, stay curious.